In this chapter, we're going to study some of the behavior of gases, and this helps us to understand things in our atmosphere and other instances when we encounter gases or gas mixtures. The gaseous state is the most mobile state of matter, and it has molecules that move at very high velocity, and they have a very high kinetic energy. So if you just imagine the gas particles, they're just bouncing all around, and we'll talk a little bit more about that. So there's four physical properties that we often need to measure to help us to describe a gas, and those four are pressure, volume, temperature, and amount. So when we're working with equations, what we'll see is that they don't always write out the words. They'll use symbols, and pressure is going to be a capital P, volume is a capital V, temperature is a capital T, and the amount is N. Now, in terms of knowing not just the properties, it's oftentimes helpful to know the common units that are used. And pressure uses units of what we call atmospheres, or ATM. Commonly in this class, we'll also see millimeters of mercury and torr. Now, you may encounter other units, like you may encounter pascals, or you may notice on your car, the tire pressure on your car is in pounds per square inch, or PSI. But for us, atmospheres, millimeters of mercury, and torr are usually the ones that we will find that where our pressures are measured in. And volume will be in a metric unit. It's usually going to be in milliliters or liters. And then we have temperature. And I'm actually going to change my pen color on temperature because it's so important. Because temperature has to be used, when we're using temperature in gases, we have to use Kelvin. Now, if you recall, to get to Kelvin, we're going to take our degrees Celsius and add 273. More specifically, it's 273.15, but if you add 273, you should be able to get your answers. So remember, in this chapter, temperature has to be used in Kelvin, the unit of Kelvin. If you do everything right, but you've used Celsius, you're still going to get the incorrect answer. And then the amount, while it may be given in grams, usually when we're using it in our equation, whoops, I didn't want to use red here, we will have to be using moles. All right, so one of the things that you can do as you begin this chapter is to recognize the four physical properties that describe a gas, along with the units that we associate with them. Now, let's first, before we move on to some of the theory behind gases, let's first talk about pressure. So this is a property that we haven't really dealt with up until this point so much. And so pressure is defined as the force per unit area. And where pressure comes from is from the gas molecules colliding with the walls of the container. So there's several things that can affect the pressure of your system. They include the number of molecules. So the more molecules you have, then the more collisions you'll have with the sides of the container, and the pressure would go up. So if you increase the number of molecules, you would also increase the pressure. You also can change the pressure with the temperature. Now, temperature is directly related to the energy of the molecules, and so if you increase if the temperature increases, the kinetic energy, or the motion inside the gas, will increase. That would create more collisions on the sides of the container and higher pressure. So an increase in temperature would also increase the pressure. And then the volume of the container, that's the size of the container, how much gas could fit in. Or not really how much gas, it's really just the size of the container. So if you take the same amount of gas and you put it in a smaller container, the pressure is going to go up. It has an inverse relationship. If you took that same amount of gas and put it in a larger container, then the pressure is going to go down. If you think about it, if you had the larger container, the gas would have more space to move around, and you would have fewer collisions with the sides of the container. So the size of the container, you have an inverse relationship, which means that if you increase the volume, you decrease the pressure. We'll look at some of the gas laws that help us see those that bit of information in a little bit different way. Then we also, oftentimes, because we have these different units, we may have to convert between the units, and to do that we would need to know the conversion factor. So you can see 1 atmosphere, which is a standard unit for pressure, abbreviated ATM. That is equivalent to 760 millimeters of mercury. And 1 atmosphere is also equivalent to 760 torr. What it also means, you may be thinking that a millimeter of mercury and a torr have equivalent sizes, and that's correct. So 1 torr equals 1 millimeter of mercury. So if you need to convert between one of these 3 units, those are their conversion factors. If in a homework problem you have one of the other pressure units, you can find the conversion factors either online or in a table in your textbook. So the kinetic molecular theory was generated in the late second half of the 19th century to formulate a general theory to explain the behavior and properties of gases. So kinetic molecular theory, also abbreviated KMT, will explain the general behavior and properties of gases. The behavior that's described is actually the behavior of an ideal gas. So ideal gases are actually don't exist, but under certain conditions of temperature and pressure, real gases approach this ideal behavior or only show small deviations from it. The benefit to this is that you'll see when we use the ideal gas model, the mathematical equations that we encounter to describe our gases are actually quite simple. So we're glad that we can describe gases as ideal gases, and that's a good approximation. Now, the kinetic molecular behavior is based on the motion of the particles of the gas. So let's take a look at some of an outline of the kinetic molecular theory. So here it is outlined in 6 points. Sometimes, depending on what you look at, they may vary the number, but it should all have these similar kind of ideas. So this is how we view gases. The gases consist of tiny particles, that the distance between those particles is very big compared to the actual size of the particle. And so if you think about it that way, the volume of a gas is mostly empty space. I always imagine this because we can walk easily through air because there is mostly empty space that we're walking through. The gas particles have no attraction for one another, which is actually pretty important. We haven't talked about the attractions between particles, but in the next chapter we'll start thinking about those forces, which we call intermolecular attractions. Number 4, the gas particles move in straight lines, colliding with each other and the walls of the container. They consider these collisions elastic, which means they might hit each other, but then they would just bounce off, and there would not be any, as number 5 says, there's no energy lost by the collision of the gas particle with another gas particle or with the walls of the container. So, then number 6 says The average kinetic energy is directly proportional to temperature and Kelvin. So for any given gases, it's the same for all gases and all mixture of gases. The average kinetic energy for the particle is the same as long as the temperature is the same. And if you change the temperature, the energy is directly proportional, which means it moves in the same direction to the Kelvin temperature. So that what the last one says is if we increase the temperature, we increase the at the average kinetic energy of the gas particles. And notice for not any of these points, all of it doesn't depend on what gas it is. These are very general ways for describing a gas.